Hello everyone and welcome back to my channel. In today's video we are going to continue our discussion on linear algebra and talk more about vector spaces. And this series of video lectures on linear algebra cover the whole UPSC math syllabus of linear algebra, and plus it will cover some additional topics regarding college level linear algebra. So please stay tuned and watch all videos and let me know with any feedback or suggestions. So in the last video, we talked about complex numbers, we defined them and saw what the properties of complex numbers are. We talked about the notation f, and to end the last session, we talked about lists and also saw the different arithmetic operations on lists. And in today's video, we are going to talk about vector space. We will define what a vector space is and see its properties. We will talk about the notation f to the power s. We will talk about subspaces, we will define subspaces, and to end our session today we will talk about sum of subspaces. Specifically we will talk about direct sum. So let's begin. So today we are going to begin our discussion with vector spaces, and again I will be attaching this PDF along with my video in my description for your reference. So what is a vector space? So vector space is a set V such that it is closed, and here the term closed is really important, closed under finite addition and scalar multiplication. So it is a set V such that it is closed under finite addition and scalar multiplication. Now most of you might know what the term closed is, but let me just explain if some of you are not familiar with that. So the term closed means if we are going to talk that there are two elements u and v that belong to a set, then the sum also belongs to v. So if I were to give an analogy in real numbers, then we say that for two real numbers a and b, we know that the sum will be also in real numbers. If example we take a as 1 and b as 2, then a plus b is 3, and we know that 3 belongs to real numbers. So which means that the set of real numbers is closed under finite addition. So for a set to be a vector space, it has to be closed under finite addition and scalar multiplication. It means for an element in a vector space, if we were to multiply it by a lambda, it has to be in V such that lambda belongs to the set F, any complex or real number. Again, giving an analogy with real numbers, if we have a in real number and we have a lambda such as 1 which belongs in F, then we know that lambda times a also belongs to real numbers. So this is what closed means, that if you add two elements of the set, then that sum is also a part of the set, and if you do any scalar multiplication on an element of the set, the resulting multiplication is also a part of the set. This is what is meant by the term closed. So this is the formal definition of a vector space. Now let's see some of its properties. So it is clearly evident that it should be commutative, and these are really easy to prove as well. So again, trivial proofs, I'm not doing them here. If you want, you can let me know, I will show you how to prove. U plus v equals to v plus u for all u and v belonging to the vector space V. Second is associativity, that u plus v plus w equals to u plus the sum of v plus w for all u, v and w belonging to the vector space V. And associativity also works for multiplication. So u times v times w is same as u times the product of vw for all u, v and w in the vector space. Then we also have the additive identity. Such that there exists we write it this way: there exists a 0 in the vector space V, such that 0 plus V equals to V for all V belonging to the vector space. And since we have an additive identity, we also have the additive inverse. The additive inverse is we have that for every V belonging to the vector space, there exists we can say minus V or U, such that V plus U equals to 0. And we can say that U equals to minus V. We can denote it as minus V, or there exists a U. Basically, we have some negation, so that we add the two numbers, we get a 0. And then we also have the multiplicative identity, and then the multiplicative inverse as well. So multiplicative identity, we know that 1 times any V is equals to V for any V belonging to the vector space. We also have the distributive property. And the distributive property is A times U plus V equals to A times U plus A times V. And it goes here: A plus B times U equals to A times U plus B times U for all A and B belonging to F and U and V belonging to the vector space V. So these are the properties, and you can easily prove them as well. Now, one thing that we often hear is the term vector or the term point. Whenever we study linear algebra, these two terms are really very common. So what a vector or a point really is: so it is basically an element of a vector space. So the element of a vector space is either called a vector or a point. So for example, R2 we know is a vector space, and R2 is the Cartesian plane, the xy plane, and any element of it, such that 1 or 1 comma 2, or we have minus 3 by 2 comma minus half. We know that these 2 points lie in the set R2. They are elements of the set R2, and we can just call these things as points or vector. So whenever in geometry we refer to the point, any point like origin or the point 1 comma 1, we are referring to the point or the vector which is the element of that set or the element of that vector space. And just a small definition regarding real vector spaces and complex vector spaces. So what a real vector space is: a vector space over the set of real numbers is called a real vector space. And similarly, we have a complex vector space, that is a vector space over the set of complex numbers. The next thing we are going to talk about today is this notation f to the s. And what does this mean is, so we have, if there is a set S, then the term f to the s denotes the set of functions from S to f. It means it denotes the set of functions from S to f, which means the set S is the domain of the function and the set f is the range of the function. It is a mapping from S to f, and the set of all such functions is denoted by f to the s. So for example, if we have r to the 0 1, we know that this 0 1 is a set. So this is the set of all real valued functions that lie between 0 to 1. It means the domain is 0 to 1 and the range is real numbers. And since we have talked about this notation fs, let's talk about the addition and scalar multiplication in this thing. So the addition, if we have two elements f and g as a part of fs, then the sum f plus g of that function is defined as f of x plus g of x. We have seen this in calculus when we see composite functions, and for all x belonging to the set S. And then we talk about scalar multiplication as well. So here for all lambda belonging to f and in f as an element of fs, then the product lambda f of x is defined as lambda times f of x. Really easy, we have done this a lot of times for all x belonging to the set S. And one thing is that the sum also belongs to the set fs, and over here the product also belongs to fs. It means that it is closed under finite addition and scalar multiplication. And by the definition you can easily verify this thing, that fs is a vector space, because the way we have defined addition and scalar multiplication on it, we know that these are closed, and if the finite addition and scalar multiplication is closed, then we say that such a set is a vector space. So fs is a vector space. Now one property regarding vector space is that vector space has a unique additive identity. A really important property to remember, and let's prove this thing. So for a normal additive identity, we know that there exists a 0 within the set, such that if you add 0 to an element of the set, the element of the set just remains the same. So let's assume that we have 0 and 0 bar be the distinct additive identities. This is the proof that it only has one. We are assuming that it has two, and then we'll come up with a contradiction that 0 and 0 bar be distinct additive identities of a vector space. So we can write this 0 bar as 0 bar plus 0. So we know that 0 and 0 bar both are an element of the vector space. So this 0 bar is being treated as an element right now, and the 0 we are just adding it over there, and this thing is same as 0 plus 0 bar. Basically adding 0 to 0 bar, such as like adding 0 to an element or adding the 0 bar to the element, we are getting the same thing, which is 0. So here we are talking about the element, here this is again the element, here this 0 refers to the additive identity, then here this 0 again refers to the element of the set, and this 0 bar refers to the additive identity, and here this is the element again. So we are starting with an element, an arbitrary element 0 bar, and we are adding. So when we start with this thing, we are adding the additive identity such that we know it should be same, and this thing is same as writing that we are adding the element 0 with the additive identity, which means that we get back the element, and this shows that 0 bar equals to 0. It sounds really weird to talk about the two separate zeros, but we are just assuming that we have two separate zeros, and that's why we are coming up with this contradiction, which means that there can only be one additive inverse, which is quite intuitive as well, that there cannot exist two separate zeros, there is only one additive identity. So this is the proof. One another thing is that for vector spaces, each element has a unique additive inverse. Again, it sounds very intuitive, but we'll do this proof as well. So let's have that U is an element of the vector space V, and assume that we have V and V bar as the distinct additive inverses of U, which means that you can write V as V plus 0, and 0 can be written as U plus V bar, because we know that V bar is an additive identity. So one thing we know is that U plus V bar equals to 0 and U plus V equals to 0, since we are defining it to be the additive inverse of U. So we can write 0 as the sum of U plus its additive inverse, and we know that the addition is associative for any vector space. So this thing can be written as V bar plus the sum of V plus U. And again, since V is defined as the additive inverse, we know that V plus U is 0, which means this is V bar plus 0, and since 0 is the additive identity, this gives us V bar back. So we know that V equals V bar, which means it cannot have two distinct additive inverse. There exists only one or a unique additive inverse. And whenever we talk about vector space, like if V is an element of the vector space, we know that negative V is denoted as the additive inverse, and if we have two elements U and V, and we talk about the subtraction U minus V, it can be written as U plus the additive inverse of V. We might have seen the same things when we studied about real numbers in 5th or 6th grade, but now we are just talking about vector space. Same definition, same things, but for vector spaces. And for all vector spaces, this is one more important point to remember, that for a vector space there is an element, not that there is an element, we say that for an element within a vector space, 0 times that element is 0. For every element, if we multiply it by 0, we get back the 0. And here again, 0 refers to the scalar 0. Like whenever we see these terms, so this 0 is the scalar 0, and here this 0 is the vector 0. For example, if we had V as 1, 2, 3, and if we perform this scalar multiplication, we get 0, 0, 0. So the 0 over here is the vector and the 0 over here is scalar. It is really important to distinguish the scalar and the vector 0, and it would be evident from the way it is written. So here a scalar 0 times any element of the vector space is 0, and then there is one more thing, that there exists a 0 in the vector space such that a number A times 0 is 0 for all A in F. So here both the zeros refer to the vector 0. For example, if we take the A as number 1, so 1 times 0, 0, 0 is the vector 0, 0, 0. So here both the zeros refer to the vector 0. And the proof of these two is really simple, so I'm leaving it. It's a really trivial proof, but again, if you want to see the proof, let me know. Now we will start our discussion on subspaces. Subspaces will be really important in, like, vector space and subspaces will be really important in our next videos as well. So right now whatever we are doing is setting up a base, just a base knowledge of definitions and properties for all the topics that are going to come, and in the topics that we are going to learn after, we will use these definitions of subspace, vector space, how addition and scalar multiplication is defined, how we have the 0, the vector 0, scalar 0. All these things will be used later on. So right now this might feel boring, like talking about definitions and properties, but this is the base and we have to make it really strong, because things really get confusing as we go forward in linear algebra. So let's define subspace. So what is the definition of the subspace? So if we have a subset U of the set V is called a subspace. It is called a subspace of V if U is also a vector space. It means that if U is a vector space, if U is closed under finite addition and scalar multiplication, and it is a subset of V, then we can say that it is also a subset of, it is also a subspace of V. For example, if we say that V, for example, if V is the space R cubed, and we say that U is the point 0, 0, 0, just a single point, then we know that this U is definitely a subset of V, and we can also see that U is a vector space because U is closed under finite addition and scalar multiplication. The only element in U is that the element itself. If you keep on adding the element, you still get 0, 0, 0, which again is an element of the set u and multiplying anything with 0 0 0, it stays 0 0 0. So again it is an element of u. One thing is, if we talk about, if we take the example that u is R3 plus, which means only positive numbers, then we know that u is definitely a subset. Here we know that u is a subspace of V, but here u is not a subspace because it is a subset, but it is not closed. Because if we have a lambda equals to -1, then any element u over here will become negative u, which is not a part of the R3 plus. R3 plus means all positive numbers. It means it is not a part. It means it is not closed under scalar multiplication. It is closed under addition, but it is not closed under scalar multiplication. It means u is not a subspace. There are millions of examples of subspaces and sets that are not a subspace. This was just a small example. There are many other, and it is really easy to show if it's a subspace or not. You can just see if it's closed under addition and scalar multiplication. If it is closed, it is a subspace. If it is not closed under either addition or scalar multiplication, it is not a subspace. And this is the definition of subspace, but there are also three conditions that satisfy a subspace. The first of them, conditions for subspace. So you can also satisfy these conditions and make sure it is a subspace or not. We say that the additive identity exists in the subspace. U is only a subspace of V if 0 is in U. The second condition should be closed under addition, which we already talked about, such that for two elements U and V belonging to the subspace U implies U plus V is also a part of U. And third thing we talked is closed under scalar multiplication. It means that for a lambda in F and U in the subspace U, lambda times U also belongs in U. So these are the three conditions. If you can satisfy these three conditions, then any set is a subset, is a subspace. If any of these conditions is not satisfied, it is not a subspace. And there are many examples of subspaces showing if it's a subspace or not, and I'm planning to solve some examples and some questions and have specific videos regarding just questions. So please do watch that video if you have any questions, or let me know for some suggestions if you want to see a specific example being solved. Next, we are going to talk about sum of subsets. So the way it is defined as, we have like, suppose we have u1, u2, so on until um be the subsets of a vector space V. Whenever I denote a capital V, it is implied that it is a vector space. Every time I'm not going to write vector space V. Then we say the sum of u1, u2 and sum of the all subsets is basically all possible sums of elements of the subset. It is not very clear by the definition what it means, but if we were to talk regarding the sums. I'm going to give more example and we'll talk about this more in this video. So this means that it is u1 plus u2 plus so on till um, such that u1 belongs in the set u1, so on. It is this set. It is really vague from the definition, so let's talk more about the sum of subsets. So if we say that, let's see a small example. If we say that U be the set of all elements of F3 such that second and third element of the set U is 0, and we suppose that W is the set of F3 whose first and third element are 0, then we can write U as x comma 0 comma 0 such that x belongs to F and this whole thing belongs to F3, and also we have this W such that we have 0 comma y comma 0 for y belonging to F, and this is also a part of F3. Then the addition of U plus W would be x y 0 for all x and y belonging to F. It means all possible sums of all possible elements would be this sum U plus W. Now we are going to talk about a really important proof. So this is the axiom that sum of subspaces is the smallest containing subspace, and we are going to prove this as well. Really important proof, and these will set up the basis of proving things later on in this chapter as well. So let u1 u2 um be subspaces of the vector space V. Then u1 plus u2 plus up till is the smallest subspace of V containing all the subspaces u1 through um. And this is the basis of where we get the term direct sums. So please follow the proof. And one thing that you can easily see is that 0 will be a part of the sum. We know that since each ui is a subspace where I is between 1 to m, we know that for a set to be a subspace, 0 should be a part of the set. So if we add all the zeros from all the subspaces, this thing holds true, that 0 is the element of the sum of all the subspaces. And we can also clearly verify that it is closed under addition and scalar multiplication. This thing, if we take an element from each of these sets, we know that it will be a part of the sum, the way the sum is defined, that it is the possible sum of each element. It means that if we take any element from any set and add that, it is a part of the set of the sum. So we know that it is, the definition itself tells us that it is closed under finite addition. And again, from the definition we also know it is closed under scalar multiplication. So if we have this thing, this is also a part of lambda times u1 till um, which means it is again closed under scalar multiplication. So this thing says that the sum of subspaces u1 plus u2 plus till um is a subspace. We have proved that it is a subspace because we have satisfied the three conditions, that additive identity is a element of the set, it is closed under finite addition, and it is closed under scalar multiplication as well. And one simple thing that we need to talk before we complete the proof is that the whole sum is contained within itself. It means that if we talk about the sum of such elements, where if we have this not equal to 0 and all other elements be 0, then we know that the whole sum, the sum of this thing u1 plus u2 till um, is again a part of the subspace, which is the set of the sum of all the subsets. Which means that it is the smallest subspace possible. There cannot be a subspace bigger than this. The proof is really vague, but if you need any clarifications, feel free to comment below or let me know. The next thing we talk about is direct sums. So if we have u1, u2, be subspaces of V, then every element of such subspace can be written in the form of it can be written as u1 plus u2, such that these small u's are an element of the subspace this. And from here we say that the sum of u1 u2 such that the sum of these subsets is a direct sum if each element of u1 u2 till um can be written uniquely, which means it can be written in only one way as the sum of elements of that subset, where each of these small u's is an element of the bigger set, capital U. And if it is a direct sum, then the way we denote is, if this thing is a direct sum, then U1 we do plus and give a circle. This is how we denote the direct sum, is denoted as direct sum. It means if the normal sum of the subspaces is a direct sum, we just have the plus and circle to denote that it is a direct sum and not just a regular sum. So this is all I got for today, and in the next lecture I'm going to show the proof, the conditions in which the direct sum holds, and then we will continue our discussion and talk about finite dimensional vector spaces, and we will talk about span, linear independence, basis and dimension of that. So this video and the video prior to this one set the basis for all the things we are going to talk in detail in the next videos. So please view these videos, and if you have any questions, do let me know. Thanks for watching. Please do like, share and subscribe to never miss a notification.